Hello, this is Mr. Precella discussing some probability theory with my online Math 1332 class. And today we're discussing complements and unions. Now, the complement, if you read through your readings, hopefully you did, and watched the Pearson video, complement is not, if you have event E, then the complement would be not E. And if you added an event and its the probability of an event and the probability of its complement together, you should get 100% or just the number 1. So the probability of an event plus the probability of its complement should give you 100% or just a 1. In problem number 1, the probability of surviving a head-on car accident at 55 miles per hour is 0.066. What's the probability of not surviving? Well, these two probabilities should add together to give you a 1, so just 1 minus 0.066. That would be the probability of not surviving. 0.934. So there's a 6.6% chance of surviving, a 93.4% chance of not surviving. Sometimes people think of these or understand it better thinking in terms of percent, just because that's usually how you hear probability. If you're watching the Weather Channel, oh, there's a 25% chance of rain, okay? They don't say the probability of rain is 0.25. Usually you hear probability with percents, but we're working with them with as fractions and decimals. A hamburger franchise is giving away a batch of scratch and win tickets with the chance to win an order of French fries. Oh, okay. There is a 1 in 20 chance that you'll win. So what's the probability that you do not win? Well, 1 minus 1 over 20. You could think of this 1 as 20 over 20 minus 1 over 20. That's going to give you a 19 over 20. Type a integer or simplified fraction. It sure wouldn't be an integer, so there's your simplified fraction. Number 3, a pair of dice are rolled, and let's see, what's the probability of getting a sum less than 8? Okay, the last time we did a problem with a pair of dice, and I wrote out all the outcomes. I also referred you to a table that's in, I believe it's View an Example, maybe even in the book, which is even nicer, where it's written out like this. So let's see. A pair of dice is rolled. What's the probability of getting a sum less than 8? Well, a sum less than 8, that would be a sum of 2 through 7. Well, altogether, if you roll those 2 dice, there are 36 possible outcomes. Well, how many ways could you get a number less than 8? That would be a sum of 2 through 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So there are 21 ways you could get a sum of 2 through 7 out of 36. We could reduce that to be a set. Let's see, divide both of those by 3, and what would we get? A 7 over 12? Oops. Number 4 says, 2 coins are tossed. What's the probability of obtaining at least 1 heads? Problem number 4. If 2 coins are tossed, let's write out all the possibilities. If you're going to toss 2 coins, you could get 2 heads, a heads and a tails. Let's think of maybe one's a nickel and one's a quarter, so you can tell them apart. Or a tails and a heads, or 2 tails. So what's the probability of obtaining at least 1 heads? Well, there's 4 possibilities altogether. How many of them have at least 1 head? Well, 3. So the probability of obtaining at least 1 head is 3/4. Okay? Now, the next one, number 5, what's the probability of getting either a diamond or an ace when drawing a single card from a deck of 52 cards? Well, the last time we did a problem with a deck of cards, and there was this little picture here. So what are we trying to find? I'll refer to this deck of cards right here just so we have something to look at. Number 5 says, what's the probability of getting either a diamond or an ace when drawing a single card? Well, you've got to be careful. You don't want to count anything more than 1. So if we look at a deck of cards, the probability of getting a diamond, well, there's 13 diamonds and there are 4 aces. But wait a minute. Okay, when you say there are 13 diamonds, that's counting one of the aces. So there's 13 diamonds plus 3 other aces, all out of 52 cards. So that would be 16 out of 52. And we could divide each of those by 4 to get 4 over 13. So back to this problem number 5. What's the probability that the card is either a diamond or an ace? 4 over 13. Okay. Now, what we've just done there, the way we didn't count this ace twice, okay, the way we didn't count this ace twice, that tells you something. It's a fundamental principle about probabilities of unions. The probability, where's my black pen? Oh, I've lost my black pen. The probability of A union B is the probability of A plus the probability of B minus the probability of A intercept B. That means if I were going through and saying, okay, there are 13 aces, 13 diamonds, 4 aces, but don't count this one, the one that's in the intersection. Don't count it twice. That's why I say minus. And we're going to use this to do some of these problems. Like number 6. Let's see. Number 6. Assume that A and B are events. We're told the probability of A union B is 0.6. The probability of A is 0.4. The probability of B is 0.55. we want to find the probability of A intersected with B. Okay? So, this is going to be a little elementary algebra that pops up every now and then. In order to, I'm going to solve this as if it were a variable, but let me go ahead and add 0.4 plus 0.55, that's a 0.95. So some of you could probably just look at it right now and think, without doing any more algebra. Think of these as percents. 95% minus what would give us 0.6 is what percent? 60%? So thinking in terms of percentages. 95% minus 35% would give you 60%. If you don't want to do it like that, if you remember some elementary algebra, here's what I would do in an algebra class. Since I'm trying to get this by itself, since there's that minus, I'm going to move this across, which is going to change this minus to a positive. And then I'm going to move the 6 over, which means subtract, the 0.6. 0.6. So we have the probability of A intersect B is 0.95 minus 0.6, which is 0.35. But again, I think just using that purple statement and thinking of it as percentages, you can just use what you know about subtraction. 95% minus 35% would give you 60%. Okay? So 0.35. Let's see. Number 11 is another similar problem. Let me go ahead and write down that fundamental rule. The probability of A union B is the probability of A plus the probability of B minus the probability of its intersection. So plugging in 0.6 for A union B, 0.4 for A. Hey, probability of B is what we don't know here. Minus A intersect B is 0.15. So let's see. We'd have 0.6 equals, I'm going to go ahead and 0.4 minus 0.15, 40% minus 15%, 25%, so 0.25. If you need to, use your calculator. So thinking in terms of percentages, I bet you could figure out B right now. 25% plus what would give you a 60%? Well, 25 plus 35? Oh, is this another 35% like on the one we just did? Number 6, yeah. Or if you want to do algebra, since there's already a plus here in front of the thing we're looking for, all I do is just move the 0.25 over by subtracting. 0.60 minus 0.25. If you punch that in your calculator or do it in your head, you get probability of B is 0.35. It's just a coincidence. Both of these problems had the same numeric answer, 0.35 or 35%. Oh, long. I got a long one. Let's see. One of those tables. The table below relates the amount of time consumers spend shopping on the internet per month with their annual income. And notice we have all the total columns. So altogether they're looking at 1,565 people. They've surveyed that many. What's the probability that a randomly selected customer either spends 10 or more hours on the internet per month shopping on the internet, or has an annual income below $40,000. So we don't want to count anything twice. Okay? So what's the probability that the randomly selected customer either spends 10 plus hours? That would be how many people spend 10 or more hours on the internet? Well, there's 444 of them. Or has an annual income below 40,000. Below 40,000, how many people have an income below 40,000? Well, 579. But we can't just add these two numbers together, because if we do, we're then counting the 118 twice. So here's what we're going to do. There's 579 people that have an average income or annual income below 40,000. There's 444 people that spend 10 or more hours shopping online. But we counted the 118 twice. That's in the intersection. So I'm going to subtract it. So we're not counting it twice. All over, how many people altogether? 1,565. So where is my calculator? 579 plus 444 minus 118. That's 905 out of 1,565. We're told write it as a decimal rounded to two places. So 0.578, would y'all call that 0.58? So there's a 58% chance of choosing a person at random that either has an annual income below 40,000 or spends 10 or more hours per month shopping on the internet. Number 9. An employee at an electronics store receives both a salary and a monthly commission. The following table lists her estimates of the probability of earning various commissions next month. What is the probability that the sales representative will earn at least $1,000? Well, at least $1,000 would be $1,000 or more. So we could add all of these up, or the sum of all these probabilities has to be 1 or 100%. So if you didn't want to actually punch all of these into your calculator, well, there's only a 5% chance that she'll earn less than 1,000. So you could say 1 minus 0.05 or 0.95, or just add these up and you'll get 0.95. So you could do it two ways. Add up all of these, and then with your calculator that should be very easy. Or 1 minus 100% minus 5%, 95%. Number 10, same type of problem. What is the probability that the sales representative will earn no more than $11.99 in commissions? Well, what would no more than $1,199 be? Excuse me, what would no more than $1,999 be? Well, that would be $19.99 or less, okay? So here, you add up those numbers. So using my trusty little calculator, I'm going to add those up. 0.07 plus 0.11 oh, the glare's bad, plus 0.23 plus 0.33 plus 0.15, but y'all know how to add numbers on your calculator, and you will get 0.89. Can y'all see that? All I've done is added up these numbers here to get 0.89. If we add up the other three, that would give you 0.11. Should add up to give you a 1, and it does. 89%, let's see, 11% is 100%. Last problem. Windshield wipers on a car have not been working properly. The probability that the car needs a new motor is 0.65%. The probability that the car needs a new switch is 0.4. I said 0.65%, I mean 0.65 or 65%. The probability it needs a new switch is 0.4. The probability that the car needs both is 0.2. What is the probability that the car needs neither a new motor nor a new switch? Well, I'm going to work this problem using that statement that we were using earlier about the probability of a union. It's the probability of A plus the probability of B minus the intersection. I'm going to let A be that it needs a new motor. And we're told that the probability that it needs a new motor is 0.65. Now B is going to be that it needs a new switch. And the probability of B is 0.4. The probability that the car needs both. Needing both, that would be an intersection, is 0.2. So what is the probability that the car needs neither? Well, from what we're given and what we have up here, we can calculate the probability of A union B. It's the probability of A plus the probability of B minus the probability of the intersection. 0.65 plus 0.4 is 1.05. Minus 0.2 is 0.85. That's the probability that it needs either a new motor or a new switch, but that's not what it's asking. It wants to know what's the probability that the car needs neither a new motor nor a new switch. Well, let me find my black pen. That's what I'm going to write this answer in. Okay, so the probability of neither A nor B. Well, the probability of an event and its complement. Either it needs one of those or it needs neither of those. These two have to add together to give a 1. So if the probability that it needs A or B is 85%, the probability it needs neither a new switch nor a new motor is 15%, 0.15. Okay? Well, we're out of time. There's people in the room or out in the hall waiting for me to get out of this room, so I'm going to have to call it quits here. Thank you for watching, and this was another section over probability theory involving unions and complements. This last problem here, very good one. It involved the union and it involved the complement. Okay? So be sure to read through your book and watch the videos and work on the problems. Don't delay, don't wait until the last moment to try to do the homework, because that's not the best way to learn. Try to stay caught up as we go through all of this. Thank you very much, and bye-bye.